Hi. So in this video, I'm just gonna kind of talk through the solutions to number 13 and number 14 in the packet. If you want to try some of it first before listening to my explanations, maybe that's a good idea. Up to you. This category here, it says area, volume, and miscellaneous. It is kind of a miscellaneous category here. So in this problem, we're given three functions. F, G, and H are twice differentiable. That means they're also they're continuous. Their derivatives are continuous. And then we're told G of 2 is H of 2 is 4. We're given a tangent line to both graphs of G and H at x equals 2. And so like we talked about yesterday, if it's tangent to, if we're given a tangent line, that slope is like the value of the derivative at that point. So knowing this, or we now know that G prime of 2 is 2/3 and H prime of 2 is 2/3. Okay. We also know it goes through the point 2, 4 because of that. The G of 2, H of 2 is 4. Okay, so find H prime of 2. Well, that's what we just talked about. So if it's tangent, if the line y equals 4 plus 2/3 x minus 2 is tangent to the graph of H at x equals 2, then H prime of 2 is 2/3. That's part A. In part B, let A be the function 3x times h of x. Write an expression for A prime of x. Find A prime of 2. It's almost, I feel like, nice of them to say write an expression for A prime of x. They don't always do that. They might say find A prime of 2, and you'd be expected to write an expression for A prime of x. You always got to do the derivative first. I'm hopefully saying that a lot because I want to make sure you don't miss that step. Okay, so A prime of x, this is going to be product rule. I got 3x cubed times h of x. That's my f and g. F prime g plus f g prime. So that's where I'm going to get this here. And I don't know anything about h, so when it's just like the g part of the product rule, I just write h of x. When it's the g prime part, I write h prime of x. And now I can plug in 2. For x's, just is 2, and then h of 2, we are told is 4. And h prime of 2, we've figured out is 2/3. Leave it there. Boom, done. Okay, let's look at part C now. This one's a little trickier. It's a good one though. So we've got, let's read through it. We've got this function h of x, we're now told is x squared minus 4 over 1 minus f of x cubed, as long as x is not equal to 2. It's also known that this limit, as x approaches 2 of h of x, can be evaluated using L'Hopital's rule. Use the limit to find f of 2 and f prime of 2. Show the work that leads to your answers. So this is one of those ones you're like, might look at me, I have no idea how to start this. Okay. Well, it's definitely important that they say L'Hopital can be evaluated using L'Hopital's rule. The first thing we always do for limit is x approaches 2 is plug in 2. Well, we would get 2 squared minus 4 is 0 on the top, and then 1 minus f of 2 cubed on the bottom. And I don't know what f of 2 is. We haven't been told that. In fact, we're trying to find it. Well, do you remember for L'Hopital's rule, we have to either have 0 over 0 or infinity over infinity. And since the top's already 0 when I plug in 2, I know the bottom's got to be 0 because L'Hopital's rule must work. So that's like the first realization is like, oh, okay, the top's 0, I got to make the bottom 0. It means I can solve for f of 2, right? If I split the limit to the top equals 0, then also the limit to the bottom must equal 0. So when I plug in 2, I'm going to equal 0. That means I can solve for f of 2, and you get f of 2 as 1. Okay, I've already found f of 2. That's probably a point. Great. All right, we're collecting points. Now, f prime of 2. Well, they tell us, like, L'Hopital's rule works. So let's use it. We would do the derivative of the top and the derivative of the bottom. And that's where, like, in my work here, I've got 2x, that's the derivative of the top. Negative 3 f of x squared times f prime of x, that's the derivative of the bottom. Okay. And we can plug in 2, we can evaluate it. Top becomes 4, the bottom becomes negative 3 f of 2 squared times f prime of 2, which is, we know f of 2 is 1, but we still have the f prime of 2, which is what we're trying to find. And here's kind of the key. Okay, this is the limit that we're trying to find since h is continuous. We were told that at the beginning. And we know h of 2 equaled 4 from the beginning. That means the limit must equal 4 there. If it's continuous, then the limit equals the value. So I know that this limit equals 4. So I can set this last fraction here equal to 4, which allows me to then solve for f prime of 2. It's a good one. It's tricky though. And then another fun part here, part D. It is known g of x is less than or equal to h of x between 1 and 3 for x. K is this new function satisfying g of x is less than k of x is less than or equal to h of x. So k is between. It's been a long time since we've talked about it, but this should remind you of something called squeeze theorem. If you don't remember what that is, maybe look back in your notes. You can Google it as well. But basically it's that idea of, if we know we have two functions, one's smaller than the other, and we have a third function that we know is between those two, then I can, like, basically this gets squeezed in. Some people call it the sandwich theorem also. Okay, so is the function k continuous? Justify your answer. Well, we know g of 2 and h of 2 are 4. And we also know that g of x is less than or equal to k of x is less than or equal to x. So we could say g of 2 has to be less than or equal to k of 2, which is less than or equal to h of 2. And then, well, I know g of 2 is 4. I know h of 2 is 4. So k of 2 has to be between 4 and 4. Well, that means k of 2 must equal 4. And we also, like, the idea with squeeze theorem is that we can do that. We can also do it with the limits. So the limit of g of x is 4. We know that because, and h of x, we know that because they're continuous. So then we can say that the limit as x approaches 2 of g of x is less than or equal to the limit for k of x is less than or equal to the limit for h of x. And those two are 4. So that squeezes the limit for k in there. And therefore we know that the limit for k as x approaches 2 is also equal to k of 2, which is 4. So that's our check of k of x being continuous at x equals 2 by the squeeze theorem. Okay, that was a lot. Hopefully this, for the next problem, this will go a little quicker. On 14 here, we got a picture, cylinder, collects rainwater, drains out through a valve, not shown, at the bottom of the barrel. The rate of change of height, we get dh dt equals negative 1 over 10 root h. I wonder, are you thinking related rates right now? Thinking GFEDs? Because that's what I'm thinking. That's what this reminds me of. Ooh, look, they give you the volume formula. Find the rate of change in the volume of water, dv dt, with respect to time, when the height of water is 4 feet. Okay, that is good old related rates, GFEDs. I probably won't talk through all of this. You can kind of look through it. E is our equation. That's the volume. Remember, with the equation, you can plug in anything that's a constant. The volume is changing. Pi r squared h. The radius is not. This is a cylinder. The radius is always 1 here. And so I can plug in the 1. So I just get my equation to be volume equals pi times h. So your derivative is pretty simple. dv dt equals pi dh dt, and then we can plug in the given information. We were told dh dt was negative 1/10 root h, and we're also told that the height of water, like we're finding this when the height of the water is 4, so at this point we can plug in 4 for that. That's where this negative 1/5 comes in, and then, oh yeah, there's that. So dv dt equals negative pi over 5. For part B, when the height of the water is 3 feet, is the rate of the change of the water with respect to time, the height of the water with respect to time, increasing or decreasing? So to find if something's increasing or decreasing, we look at its derivative. So is the rate of change of the height, dh dt, increasing or decreasing? So I need the derivative of dh dt. It's like I'm finding the second derivative, okay, which is the derivative of the negative 1/10 root h. So I can do that. Don't forget chain rule. So you can do the whole, h to the 1/2 h to the negative 1/2 gives me that, but times dh dt, which we have, it's negative 1/10 root h. And then we are also given height is 3, when the height of the water is 3 feet. Well, actually, look at that. The root h cancels, so the negatives cancel. We just get 1 over 200. So everywhere, this is positive, barely, but it's positive. It's greater than 0, so the rate of change of the height is increasing. Part C, time equals 0 seconds. The height of the water is 5 feet. Use separation of variables. Ooh, there's like a hint for you. This is like I'm solving a differential equation to find an expression for h in terms of t. So I'm going to separate the dh dt, h, 1 over root h on the left, negative 1. Leave the constant with the dt. Integrate both sides. Plug in, solve for c, solve for h. And that's that one. So try it. Now the third problem here, so was that 15? Number 15 is a different kind of problem. It's volume. That's the things we've done most recently. So work together on it. Try it out, and thanks for watching.